Okay, hello. So I'm starting my lecture for today. So in the last class, we have discussed about okay. So we have discussed about the Sssc. Okay, the operation of the Sssc. Okay, so we have discussed about the operation of the Sssc, and we have discussed about the control rating and VA rating, control range and VA rating of the Sssc. Okay. So now we will be discussing about the capability to provide real power compensation. That means how much does the Sssc are capable of compensating the real power, not only the reactive power but also the real power, because real power compensation is also done by the Sssc. In contrast to the series capacitor circuit as a reactive impedance, because capacitor banks are actually they have a capacitive reactance in them. So when they are connected in series, okay, the series capacitors, they contribute towards minimizing the transmission line reactance. So if the transmission line reactance is decreased, that means the power transfer capability increases. Okay, because we know the actual equation of real power in a transmission line is P equals to sending end voltage multiplied by receiving end voltage divided by the transmission reactance multiplied by sine of power angle. That means the phase difference between the sending end voltage and the receiving end voltage. Okay, so this is the power transmission. So now okay, so now since the series capacitors do this function, they're actually minimizing the reactance, because when capacitors are connected in series, because this has already been explained, okay, in the previous classes, that the transmission line reactance is like this. Then if you connect a capacitor bank, okay, in series, a series capacitor, so what is happening, this is XL, this is XC, okay. So the series reactance is actually getting, because both of them are of different phasor, because the uh, if you draw the impedance triangle, okay, so in RLC series circuit we have seen that XL and XC, if they are in series, so there is a, if XL is greater than XC, so the resultant reactance will be XL minus XC. Okay, then transmission line, and the XL is greater than XC, so you will get XL minus XC. Otherwise there can be XC minus XL also if XC is greater than XL. But in transmission lines, the line reactance is huge, and the series capacitors are generally installed with a certain percentage of the line reactance, so that XL minus XC we are able to minimize the line reactance. So the transmission circuit, so it is told that in contrast to the capacitor bank or series capacitor, means this is what series capacitors does, okay, which functions in transmission line as a reactive impedance, and as such is only able to exchange reactive power, because it can only exchange reactive power. Okay, if it is connected in series or shunt, it can only exchange the reactive power. The Sssc can negotiate both reactive and active power with the AC system simply by controlling the angular position of the injector voltage with respect to the current. That means by controlling the angular position of the injector voltage. That means the Sssc is actually injecting voltage into the transmission line. So if it is injecting voltage into transmission line, it is actually injecting both active power and reactive power, okay, but not at the same time, okay, because the control of whether it will be injecting active power or reactive power, that totally depends upon the controlling the angle between the injected voltage and the line current. That means the injected voltage and line current, because line current is already present, okay, because if you see this particular circuit, one second. Okay, so if you see this particular Sssc connected in series with the line, you see that this particular line is having some current, okay, and the voltage is injected into the particular system, okay. So there is a phase difference between the injected voltage and the current. So depending upon the shifting of the angle, okay, that particular reactive or active power, whatever it is desired, it can be controlled, it can be injected, okay. So that means by controlling the angular position of the injected voltage with respect to line current, so we can negotiate both the reactive and active power into the transmission line. Okay, so however, as explained previously, the exchange of active power requires that the DC terminal of the Sssc converter should be coupled to the energy source or sink. That means there is an energy source or sink, because the energy is coming from some source, okay. So there should be some energy source or a sink also, because when it is absorbing the power, so the energy will be stored in some storage device. So there is some suitable storage, energy storage also, okay. So okay, so that means the exchange of the reactive power and active power, because the exchange of the active power rather requires that the DC terminal of the Sssc converter be coupled with the energy source. That means the DC terminal should be coupled with the energy source, otherwise it won't be able to, you know, act as a active power supplier, okay, because the DC terminal has to be connected, because the Sssc, it is actually the static synchronous series capacitor, or static series synchronous capacitor. So it is actually a power unit device, so the triggering it requires from the DC circuit, okay. So without that it won't be able to be possible for the energy supply or the storage to continue to store or supply the active power without connecting with the DC terminal. The capability of the Sssc to exchange active power has significant application potential. Is the simultaneous compensation of both the reactive and resistive components of the series line impedance in order to keep the X/R ratio high. In many applications, particularly at transmission voltage levels of 115, 230 and even 340 kV, where the X/R ratio is usually relatively low, because in those areas, in those high voltages, okay, the transmission line variable voltages, when it is actually 115, 230 kV or even 340 kV, the X/R ratio is usually relatively low, okay, in those cases, because when the voltages are too much high, okay, when the voltage are too much high, so voltage is too much high, then the current required reduces, because see, whenever you are supplying any power, suppose it is 100 megawatt or 200 megawatt in a transmission line, you are transmitting power. So the power which is transmitted is equals to the voltage into the current. Okay, so voltage into current. So now if the voltage is increased, so the current will decrease. So if the power transmission, the amount of power which is transmitted in the transmission line, if it is kept constant and the voltage is increased, so the current will reduce. Okay, so current is reduced means we will require less material for the conductor, and the inductance of the line is equals to flux per ampere. So if the current is reduced, the flux will also reduce. So flux per ampere will also totally reduce. So inductance will reduce. If the inductance reduces, the inductive reactance reduces. So the inductive reactance X reduces. So X by R ratio is low. Okay, so which is in the range of 3 to 10. So a high degree of series capacitive compensation could further reduce the effective reactive to resistive line impedance ratio to such low values at which the progressively increasing reactive power demand on the line and associated line losses and possible voltage depression will start to limit the transmittable active power. So what happens when the line reactance is already low for extra high voltage transmission lines? So if series capacitors are connected in them, so series capacitors with the intention to maximize the power flow. But what happens if the X by R ratio is already low and you are connecting series capacitor along with it, more series capacitance, so the X by R ratio will be fall down further. So if it is falling down further to such a low value that the increasing reactive power demand on the line, okay, and the associated line losses. So what happens? The impedance of the ratio of the line reduces so much that active power transfer becomes very much difficult. The active power transfer becomes very much difficult. Okay. This situation illustrated with the Phasor diagram shown in the figure 6.38 for a normal angle control line whose uncompensated X by R ratio is 7.4. Okay. So this is the Phasor diagram. Okay. So you can see this is the voltage Vx, and this is the phasor of the I current. Okay. So this is a transmission line. Suppose this is a transmission line. This is small resistance, and this is the inductive reactance of the line reactance, and this is the series capacitor. So this is the X effective. So if this is the effective reactance of the line, total reactance of the line. This is Vs. Vs is the sending end voltage. Vr is the receiving end voltage. Okay. Capital VR is the voltage drop across the resistance, and VXCFF, that is the voltage drop across the effective reactance, and I is the current. Okay, this is line current. It is the line current because it is a series circuit. There will be only one current. So as seen by the following increasing series capacitive reactance compensation, that is for example 50 and 75, the effective X by R ratio, okay, X effective means XL minus XC, okay, ratio decreases to 3.7 to 1.585 respectively. Okay, so as we can see, by applying the increasing series capacitive reactance to 50 to 75%, so series capacitive reactance, if it is increased to 50 to 75%, okay, so the line reactance that is the X by R ratio decreases to 3.7 to 1.85. So see, this is 3.7. So if this is the capacitance, this capacitive reactance is increased, okay, to 50 to 75%. Okay, to 50 to 75%. So what happens? This voltage, okay, the phasor diagram in such a way that the ratio decreases, and it is reflected in this particular phasor diagram. This phasor represents that when the effective reactance is 50%, okay, and this is the effective reactance is 75%. Remember the voltage when the effective reactance has been given by 75%, okay, for the capacitive compensation. As a result, the reactive component of the line, this is the reactive component of the line current, because the line current has active component, reactive component also, because the part of the current which is actually responsible for the or passing through the reactance. Okay, reactive component of the line is this one, line current is this one, which is I sine power angle del by 2 plus phi, supplied by the receiving end system, progressively increasing, and the real component is a real component which is passing through the resistance. So it is passing through the resistance, okay, the real component. So what happens, this particular line current of the reactive component of the line current and the active component of the line current. So reactive component of the line current increases, and the reactive component of the line current transmitted to the receiving end progressively decreases with respect to those which would be obtained with an ideal reactive line of R0. That means the reactive component increases, active component decreases. So what happens if you increase the capacitance more and more? For 50% the X by R ratio is 3.7. For 75% of the line capacitance, the capacitance is increased, capacity reactance, so the effective line reactance decreases to 1.85. Okay, so what in this case what happens, the reactive component of the line current is increasing more and more, okay, and the because X by R ratio is falling down, so X by R ratio is falling down, okay, so the resistive component is decreasing and the reactive component is increasing of the line current. So if the line current resistive component is decreasing, that means it won't be able to transmit active power anymore. The transmittable active power P and the reactive power Q supplied by the receiving end bus can be expressed for the following two meshing system. Two meshing system means this is the two meshing system where we have a alternator and we have a synchronous motor. Okay. So the two meshing system means any particular transmission line where source and sink, or you can say the receiving end side, is represented in this way. So the equation of the active power and reactive power supplied by the receiving end bus can be expressed for this simple two meshing system employing angle adjustment for power flow control at constant end voltages as functions of the actual or effective reactive line impedance X and the line resistance R and transmission angle del, okay, as follows. So which shows that it is being represented in this way, the two meshing system, okay, employing the angle adjustment for power flow control at constant end voltages. So it is considered in such a way that the angle, that the power angle, del angle, is controlled in such a way that the power flow takes place at constant voltages. The power flow takes place at constant voltages. That means the sending end voltage and the receiving end voltage would be same. The angle is tuned in such a way, so there won't be any voltage drop. So if there is any voltage drop, we are not considering that. Okay, that is why VR equals to VS equals to VR equals to V. So the active power equation will be V square by X square plus R square, because it is actually Z, where X is greater than too much higher than R, so we don't consider X R. Okay, we only consider X. But in this case, since we are using series capacitor, suppose, so X by R ratio is decreasing. Okay, so X is not too much higher compared to R, so that is why we are considering both X and R. So we are considering rather Z. Okay, this is the equation. So whatever we were discussing, this is the equation for the active and reactive power. So the normalized active power P and reactive power Q versus angle, okay, the transmission characteristics described by equations 16 and 17 are plotted by a parametric function of X by R ratio for X by R equals to infinity 0.744, 7.4, 3.7, 1.85 in the figure 6.39. So this bold line represents the active power, okay, and dotted line represents the reactive power. So this is the active power curve. Okay, so based on the X by R ratio, it is just an analysis that if the X by R ratio is decreasing, then what is the problem? What will be the problem? Because since we were discussing in this particular case that Tssc has the capability of transmitting or injecting active power and reactive power both by controlling the angle of the injector voltage and the line current, but series capacitor is only able to control the reactance of the line. Okay, so or contribute towards the reactive power. So when series capacitor is connected in the line, what it is doing, it is reducing the reactance of the line, because the line reactance is decreasing. Since the line reactance decreases, so what happens? These are the problems which come into account, that the total X by R ratio decreases. So as the total X by R ratio decreases, the reactive component of the line current increases too much, so that the active component of the line current reduces, that is the resistive component of the line current reduces, and it is unable to transfer power. So this is actually this is just the case or the study which is shown from the phasor diagram. If you want to represent the same thing in the power angle diagram, okay, so from the power equation, if we see this particular scenario, that with the respect to the power equation in 16 and 17 equation, 6.16 and 6.17, if we want to change the X by R ratio, suppose there is X capacitive reactance in such a way that the X by R ratio is changing. Suppose we take X by R ratio to be 1.85, that means we have reduced the transmission line reactance to a very higher level, so that the reactance is only 1.85 times greater than the resistance. Okay, so this is very low X by R ratio. So what is the problem? So if you put this value over here, X by R ratio, in this particular equation with respect to a constant delta, so you will get a particular graph like this lower one, because where the X by R ratio is 1.85, that means with respect to the angle delta increases, okay, increases, we get a sine wave, and decreases, so accordingly we get a sinusoidal equation. Okay, you can see it is almost 0.5 per unit of the actual power transfer. Okay, 0.5 per unit. Okay, and reactive power flow, the reactive power flow is almost constant for all the three cases, all the four cases. But the active power flow, you can see if you compare, suppose for 3.7, the power, you can see it is increased more than 0.5, so it is almost 0.7 or 0.75. Okay, now for where the X by R ratio is 7.4, if it is 7.4, then it is increased further, and if the X by R ratio is infinity, that means X is very greater than R, so we don't consider R at all. So in that condition, what happens? The power is transferred at a maximum value. We get 1 per unit active power transfer. Okay, and this first one is the graph of the reactive power flow also, reactive power flow. So this is for the 1.85. okay, and these two are actually submerging, 3.7 and 7.4, and this is for the infinity. So reactive power we are not bothered about, we are bothered about the active power. So X by R ratio should be higher for the better transfer of the active power. So the Sssc with an appropriate DC power supply, which will be power simply, for example, for an accessible bus or from the tertiary of a conveniently located transformer. So that means DC power supply where we will get, we will not use batteries, not possible. So it is actually coming from a bus, okay, or a tertiary part of a tertiary winding of a transformer. Suppose we can take from there also, because we have a three-phase transformer where we have primary, secondary, but we have also tertiary as well. So tertiary is set in such a voltage level so that it draws the power from there. Okay, So the DC, the Sssc is getting power from that particular supply. So this the Sssc with an appropriate DC supply would be able to inject, in addition to the reactive compensating voltage, a component of voltage in antiphase with that developed across the line resistance to counteract the effect of the resistance voltage drop on the power transmission. So this is the advantage of the Sssc. So it is able to inject, in addition to the reactive compensating voltage, a component of voltage in antiphase with that developed across the line resistance to counteract the effect of the resistance voltage drop on the transmission line. It is also counteracting that particular effective voltage drop on the transmission line, so that the X/R ratio can be maintained at a higher level. Okay. In this way, by providing simultaneous and independently controllable compensation of both the active and reactive and real impedance of the line, in effect an ideal reactive line can be treated or can be created for maximum power transmission. So it should be noted that the power I²R would of course still be dissipated by the physical line. However, this dissipated power would be replenished by the Sssc from the auxiliary power supply. The real power supply compensation capability would also be used effectively in minimizing loop power flows by balancing both reactive and active power flows of parallel lines. So this power flow which is coming from the Sssc can also neutralize the, or can also the power losses also. So I²R loss, transmission line loss will be there, but this Sssc will able to compensate that also. So it will be supplying additional power to the line, so that the particular power which is lost, okay, can also be replenished, or okay. So the real power compensation capability could also be used effectively in minimizing the loop power flows by balancing both the real and reactive power flows of the parallel lines. Just 1 second. Okay, so continuing where we have left. So we were discussing the advantage of the Sssc over the series capacitor. Okay, so the series capacitor, actually what it does, it reduces the line reactance in such a way that the X/R ratio reduces too much. So if the X/R ratio reduces too much, so it will result in very less amount of active power flow to the line. So active power flow of the line will reduce, okay, because the reactive component of the line current increases and the active component of the line current decreases. And from the power equation also we have seen that as the X/R ratio falls down, the power transfer capability reduces. So the power transfer capability also reduces. You can see this. For X/R ratio 1.85, the power transfer capability is very less compared to the X by R ratio, which is infinity. So the power transfer capability is almost maximum. We are getting 1 per unit. Okay. Okay, now coming to another series compensated device. We have seen that series compensated device, we have seen Tssc, okay, Thyristor control series capacitor. We have seen the static series synchronous compensator. Now this is another series compensated device, okay, which is the Tssc, which is the Thyristor switched series capacitor. So you can see this particular figure of 6.10, which is the basic Thyristor switched series capacitor scheme. Okay, so there are a lot of capacitors connected in series, but their switching is done with the help of a Thyristor setup. Okay, so Thyristor setup is used for switching the capacitors on and off. Okay, so it consists of number of capacitors, each shunted by an appropriately rated bypass valve composed of a string of reverse parallel connected thyristors. So they are actually reverse parallel connected because their capacitors are shunted and the control thyristors are connected in shunt to it, but there are two thyristors which are also connected parallel to each other. Okay, but they are actually connected in reverse direction, so it is called the reverse parallel connected thyristors. Okay, so all these connections, all the capacitors, so number of capacitors each shunted by appropriately rated bypass valve composed of a string of reverse parallel connected thyristors in series. That means capacitors are in series. The capacitors are in series. Okay, so but the control is done by shunted thyristors, and thyristors also reverse parallel connected. The operating principle of the Tssc is straightforward. That is, the degree of the series compensation is controlled in a step-like manner, okay, by increasing or decreasing the number of series capacitor inserted. So obviously the degree of series compensation is controlled by how much series compensation do we require, okay, because it is an application of the series capacitor. So you can say the SSCs are, you know, better compared to the series capacitors, but these series capacitors are also used in many cases where the voltage of the transmission line is not that much high that the X by R ratio should be affected. So the X by R ratio should not be affected. Okay, so keeping the X by R ratio within the permissible limit, okay, so that the X by R ratio is comparatively high, even though if this particular series capacitors are connected, that means from the beginning itself X by R ratio is too much higher. Okay, so if it is too high, then if the line reactance is too high, then it is resulting in huge amount of reactive power consumption by the transmission line, that the voltage at the receiving end side is falling down to a higher value. In that case, the series capacitors connections are used. Okay, but in extra high voltage line where the X by R ratio is not that much high, then series capacitors can result in reducing the X by R ratio to a further level that the active power flow is also hampered. Active power flow is not also possible to be done. That is why in those cases SSC is generally preferred for extra high voltage lining, but for voltages of lower level, okay, these series capacitors are generally used because SSCs are also quite expensive. So the SSC, the Tssc which are connected in series, the lot of capacitors are connected in series, they are actually switched on and off depending upon the requirement. Okay, so the number of capacitors which are connected are actually inserted or removed depending upon the switching. So capacitor is inserted by turning off and it is bypassed by turning on the corresponding valve. Okay, So a thyristor valve commutates naturally because the commutation is required in the thyristor valve. So it commutates naturally, that is, it turns off when the current crosses 0. So the thyristor commutates naturally, so there is no external commutation required for the thyristor. So it is being turned off when the current crosses 0. So when the current is 0, it automatically turns off. So there is no particular commutation required for that. Thus the capacitors can be inserted into the line by the thyristor valve only at 0 crossing of the line current. So that means when the thyristor valve is switched off, then only the capacitor is connected in series, because when you are connecting all of them parallel or series, okay, the current is flowing in a series in a series way, series manner, okay, in series they're traveling in series, okay. So now if you want to switch off capacitor C2, so what you will do, in that case the current has to be bypassed through the thyristor, so that no current passes through the capacitor C2. So thyristor will be switched on, and if you switch off the thyristor, it becomes open, automatically current will pass through the capacitor. Okay, so it is quite easy that if you want to switch on capacitor 2, you have to switch off the thyristor valve of capacitor 2. Okay, so in that way it is done. So see the computation, so as we were discussing that the computation is done naturally. So when the current reduces to 0, the particular current in the thyristor also reduces to 0. So hence the capacitor is turned on when the current crosses 0. So 0 crossing of the line current, the capacitor is turned on. Okay, when 0 crossing of the line current of the thyristor valve, okay, of the thyristor, not the supply. Okay. Now since the insertion takes place at line current 0, a half wave cycle of the line current will charge the capacitor from the 0 to maximum and successive, and the successive opposite polarity half cycle of the line current will discharge it from its maximum to 0. I will illustrate it in this particular figure 6.11. So when the supply is there, when the current is flowing, you can see what is happening. The capacitor current is, when the current voltage is applied across the capacitor, so there will be some capacitive current. Okay, so since the insertion takes place at the line current 0, when the line current is 0, then the capacitor takes place, is connected. So 0 crossing means what? 0 crossing means, this is very interesting, because since it is alternating current, so there is a meaning for 0 crossing. This you have also studied in the capacitor, the circuit breaker. Means where we have studied that arc quenching. Okay, arc quenching. So in that case, the capacitor used to be turned off when the current was 0. Okay, here also, when the current is at the peak, you cannot, or it is having some positive or negative value, whatever the magnitude, you cannot switch off the thyristor. So when the current is crossing is 0, so thyristor is switched off and the capacitor is connected in series. So since the capacitor is connected in series, suppose C2 capacitor is connected in series when the current crossing is 0. So it is connected when where there was no current initially. So at that instant, it is connected. Okay, that means it is told that since the insertion takes place at the line current 0, okay, a full half cycle of the line current will charge the capacitor from 0 to maximum. Okay, that means a full half cycle. Okay, that means suppose the current crossing is 0 over here. In this particular case, okay, the capacitor was switched on. So now when the current again continues in the negative half cycle, the capacitor will be fully charged from 0 to maximum on the negative half cycle itself. That means one half cycle is enough to charge the full capacitor. Okay, so it is fully charged. from 0 to maximum, okay, and the successive opposite polarity half cycle of the line will discharge it from its maximum to 0. So opposite polarity, that means if I say that this is the sinusoidal waveform of the current, okay, this is the line current, suppose. So this one, this four, okay, so all the capacitors were switched on. Now when the current was increasing like this, okay, at this zero crossing, okay, this thyristor was switched off, so capacitor was connected. So now the C2 capacitor also connected. Now when the current was increasing in the negative half cycle, the C2 capacitor gained the voltage from 0 to maximum. It was totally charged. Now again, when the current was traveling from again another positive half cycle, then it was again discharged. Capacitor was again discharged. So charging, discharging takes place at every half cycle of the, you know, at every half cycle of the waveform. Okay. So this is being shown over here. See, this is the capacitor, and this is the Thyristor setup, switching Thyristor setup, okay, which are anti-parallel connected. So current is traveling this way. The capacitor is getting charged. So the charge voltage is equals to Vc. Okay. So the current is like this. The current is traveling this way. At current crossing 0, okay, it is switched on. Okay. And when the half cycle is there, at this point, the capacitor is charged fully. So if you see, if I draw this particular graph in this way at this particular point, you see some peak values over here. At what peak value? When the current is 0. So initially when the current was started, okay, the capacitor was not switched on, it was switched off. When current crossing reached 0, the capacitor was switched on, and when the current is increasing in the negative half cycle, the current is increasing in the negative half cycle like this, and again coming to current 0. When the current was reaching the negative half cycle, it was following the negative half cycle, the voltage of the capacitor was increasing. So it won't understand whether the current is sinusoidal or not, or if it is having a peak value or not. If the current is increasing, see, at the peak value of the current, the capacitor voltage is not peak, because suppose the current RMS value is suppose 100 ampere or 10 ampere. So 10 ampere. So the capacitor will see that 10 ampere is flowing, so it is getting charged. So you know, the entire current is available from this point number A to point number B. Okay, so current is available from point number A to point number B. So the capacitor will charge during this duration. Now when the current has reversed its polarity from point A to point C, the capacitor will again discharge, and at point C it will reach the 0 value. Okay, so the capacitor voltage is 0 over here, point C. Again in the next negative half cycle, when the current will continue, the capacitor will again reach maximum voltage. In this way it will continue. Okay. Okay, so as can be seen, the capacitor insertion at line current 0 necessitated by the switching limitation of the thyristor valve results in a DC offset voltage which is equal to the amplitude of the AC capacitor voltage. In order to minimize the initial surge current in the valve and corresponding circuit transient, the thyristor valve should be turned on for bypass only when the capacitor voltage is 0. With the prevailing DC offset, this requirement can cause a delay of up to one full cycle, which would set the theoretical limit of the attainable response time of the Tssc. Okay. So this was all about the Tssc. Okay, discussion. A second. Okay. Now coming to the another pack device, okay, which is called the UPFC, which is the Unified Power Flow Controller. So Unified Power Flow Controller is basically it is a combination of the series and shunt, okay, devices. Okay, so you can say it is a combination of series and shunt devices together. So that is called the Unified Power Flow Controller. So a combination of STATCOM, that is static synchronous compensator, that is shunt, and the static series compensator, okay, Sssc, or static series synchronous compensator Sssc. That means this shunt compensator, static shunt and static series compensator, both STATCOM and Sssc, which are coupled via common DC link. So we are coupling them in a common DC link to allow bidirectional flow of real power between the series output terminals of the Sssc and the shunt output terminals of the STATCOM. That means they are coupled in such that using a common DC link, they are coupled, okay, to allow the bidirectional flow of the real power. So real power is traveling in both the directions, bidirectional flow of real power between the series output terminals of the Sssc and the shunt output terminals of the STATCOM. That means if you visualize the circuit diagram of a Sssc and the STATCOM, you see that the output terminals of the Sssc is there, output terminal of the STATCOM is there. So they are actually means when the power flow is bidirectional, that means the power flow is taking place from both the directions. So power flow is taking from both the directions. So in the bidirectional power flow, okay, which is taking place, will take place from both the STATCOM and the Sssc together from the output terminals, and are controlled to provide concurrent real and reactive series line compensation without an external electrical energy source. So there is no require of external energy source, okay. So this entire compensation will be done by them totally, okay, solely by them as a together itself. So bidirectional power flow for both active and reactive power compensation. Now the UPSC by means of angularly unconstant series voltage injection is able, or alternatively the real and reactive power flow in the line. So the UPFC may also provide independently controllable shunt reactive power, shunt reactive compensation. The controller, if you see this particular figure 5, figure, then we will be able to understand. This is the particular UPFC structure, okay, where this is the transmission line, and the STATCOM is connected shunt with respect to a transformer. It is connected shunt parallel to the line, and Sssc is connected series to the line. Okay, it is series to the line. So you can see this transformer is connected in series, but this transformer is connected parallel. Okay, and they are both connected via DC link. That means the combination of STATCOM and Sssc for the compensation of the real and reactive power. So series compensation and shunt compensation can be done simultaneously. There is a combination of STATCOM and Sssc which are coupled via common DC link to allow bilateral flow of real power between the series output terminals of the Sssc and shunt output terminals of the STATCOM. These are controlled to provide concurrent real and reactive line compensation without an external energy source. UPFC by means of angular, one second, by means of angularly unconstant series voltage injection, because there is no constant series voltage injection in the UPFC, because series voltage injection is done by the Sssc part, so it is actually unconstant, there is no constant, so it is totally done by the angle, so changing the angle. So it is able to control concurrently, simultaneously, selectively the transmission voltage, impedance, angle, okay, or alternatively reactive and real power flows. So you can say both the effect of STATCOM and Sssc can be sensed or can be visualized in this particular setup, where the real power and the reactive power are compensated in both the directions by just controlling the angle. Okay, so the STATCOM will also control the real and reactive power. Sssc will also control the real and reactive power as per the requirement. The UPFC may also provide independently controllable shunt reactive compensation. We will dig into that later on, the details of the UPFC, but before that we will just see few other fact devices. There are few other fact devices which are also worth mentioning, that interline power flow controller, the IPFC. Okay, the IPFC is there. The IPFC is actually, this is a recently introduced controller. It is a combination of two or more static synchronous series compensator. So static synchronous series compensator means the Sssc. So it is a combination of two or more Ssscs. Two or more Ssscs are combined, which are coupled via DC link to facilitate bidirectional flow of real power between the AC terminals of the Ssscs. Okay, so the bidirectional with the particular DC link they are connected. Okay, and they facilitate the bidirectional power flow. That means from both the directions. So if required, the power flow can be done from both the directions. So it is combination of two or more than two Ssscs. Okay, and this control of this reactive and real power. Okay, it is done that the controlled actually they are controlled using the DC link. Okay, they are controlled to provide independent reactive series compensation for the control of real power flow in each line and maintain the desired distribution of the reactive power flow among the lines. Thus, it manages a comprehensive overall real and reactive power management for a multi-line mission system. Okay, then we have the Thyristor controlled phase shifting transformer, TCPST. See, phase shifting transformer is also required in many cases. Okay. Okay, so a phase shifted transformer means, see, V del, okay, suppose supply voltage is del 1 and receiving end voltage is del 2. So the difference between them is called the del angle, suppose. Okay, the power angle. So this power angle is very important for power transmission, as we already know that P is equals to Vs Vr by X sine del. So if the power angle is reduced, that means if the phase difference between the sending and receiving end voltage is not adequate, then the power transfer becomes less, the power capability reduces. Okay, the power transfer capability reduces. So that is why, in order to maintain the power transfer capability at a higher value, this del angle has to be restored or it has to be increased. Okay, because in the difference between a DC power flow and AC power flow is that the major one basic difference is that in DC power flow, the power flows from higher potential to lower potential. We all know. In AC also, with AC, you can transfer the power, because see, the current will flow from higher potential to lower potential, that is obvious. But suppose I am telling to say that if you are transmitting, suppose some power, suppose 33 kV, okay, or say 132 kV DC, suppose the receiving end you will get some lower voltage, okay, suppose you are getting 125 kV because there is voltage drop. In transmission line also we will get the same thing. Suppose we are feeding 132 kV, we are getting 120 or 125 kV receiving end side. But if the line load is very less, then there is a chance of fadant effect also. So 132 kV will result in 135 kV also in the receiving end side. So voltage will increase. So how it is possible? Because the power is flowing from lower potential to higher potential because of the del angle. Because only in AC the power can flow from lower potential to higher potential because of the del angle. So this is only possible if the phase difference of the sending end voltage and receiving end voltage is positive. There is some phase difference. If there is no phase difference or negative phase difference, power will not flow. That is why this del is very important. So del 1 has to be greater than del 2. So del 1 minus del 2, more the angle, more is the power transfer capability. So in many cases, the power transfer capability is enhanced by connecting the TCPST, that is the Thyristor control phase shifted transformer. What they do, these transformers don't step up the voltage, but they increase the phase angle between the whatever phase angle is required, it adjusted accordingly. So this controller is also called the Thyristor control phase angle regulator, that is the TCPAR. A phase shifting transformer controlled by thyristor switches to give a rapid variable phase angle. So thyristor switches are there. Okay, so this is the kind of a transformer where it is thyristor controlled only for the increasing the phase angle. Next we have the thyristor controlled voltage regulator, that is the TCVR. A thyristor controlled transformer which can provide variable in phase voltage with continuous control. So phase voltage means suppose in the receiving end side the voltage has reduced too much. Okay, so we know that tap changing transformers are there. Okay, tap changing transformer also we have studied in your machines and power system also, that we have tap changing transformer like this. Okay, a tap changing transformer, so like auto transformer itself. So there are taps. Okay, so at different tappings they are connected. Okay, so if this is 100%, this is 50%, this is 25%, and so on, different taps. So suppose this is done because initially at the receiving end side it is not connected to 100% because the transformer is connected to a certain value. Suppose the transmission line voltage is 1 per unit. Okay, supply voltage Vs. Okay, and receiving end side we are supposed to get 0.95 per unit, suppose, because there is transmission loss we know. But suppose it is reduced to 0.91 per unit, then at the receiving end side this particular transformer is connected. Okay, just like a tap changing transformer. This is the diagram of a tap changing transformer. So what happens, initially the tappings are not given maximum, because if it is at the maximum height then it won't be able to increase it. So for 1 per unit itself it is connected somewhere over here, because you know that there will be some voltage drop later. So if the voltage drop is there, it will increase the tapping. Once the tapping is increased, again it will reach say 0.95 or 0.96, whatever required, it will increase. So in order to maintain the voltage, because see, power loss is there, it is inevitable, we cannot do anything for that, active power loss. But if the voltage drop is there, we can increase the voltage, because if the voltage in the receiving end side is too much lower, suppose there is a transformer, you are supposed to get from 132 kV, you are supposed to get 125 kV. So in the transformer secondary, the receiving end side, The secondary of the transformer will give you the primary of the transformer will give you 125 kV. So if the turns ratio is suppose 10:1, so you are expecting 132 kV. So the secondary you will get 13.2 kV, isn't it? 13.2 kV. That means what I'm trying to tell is that if I show over here that in the sending end side Vs is there, bus bar, then the transmission line, okay, then the receiving end side we have the load, this is Vs. Now this is 132 kV, suppose transformer is there, there is another transformer over here also, so this is expected to be suppose 10:1, this is VR, actually this is VR, 10:1. So if you get the voltage to be 125 kV, obviously the load will get 12.5 kV, isn't it? If you get 132 kV, the load will get 13.2 kV. Okay, suppose 125 kV is the standard one, because you know the load is required 12.5 kV. But suppose due to the high current, okay, more power is being transferred because the power more alternatives connected in series in parallel. Okay, so more alternatives there. So current has increased because previously it was 1 per I was suppose 1 per unit. Now the I has increased to 2 per unit. So double power is being transferred. Okay, so double power is transferred. So now we know that as per the contingency analysis, the transmission line is generally run under lower capability, because we generally don't design the transmission line and install a transmission line in a particular area so that it will be able to supply that amount of current only. No, if the current capacity is of the transmission line is say 200 kiloampere, we generally give less than 100 kiloampere, because we keep some for reserve, because if the power transfer capability increases, okay, in future we won't be able to, you know, not necessary to or not possible to change all the transmission line. So the transmission line conductor will be taken same, it will be the same, and higher current if it is flowing, then it will be able to withstand it. So that is why the conductor is carrying the current. Okay, so now the per unit value of the current is okay. Now if the per unit value of the current has increased to 2 times, okay, so what happens, the voltage drop will increase. Suppose the voltage is still 132 kV, we are not changing it. Now if the voltage drop has increased and we are getting only 120 kV, so obviously the receiving secondary side will get 12 kV only, but we want 12.5 kV. That is why in that case we use a transformer. Okay, so that another transformer is there, tap changing, because this transformer will be a tap changing one, this transformer, so that if it is 10:1, it can increase to suppose the ratio, you can decrease the ratio, okay, in that way. So you can change the ratio so that you can get the desired voltage. Another device is the interface power controller, IPC. Okay, so a series connected controller of active and reactive power consisting in each phase of inductive and capacitive branches subjected to separately phase shifted voltages. The active and reactive power can be set independently by adjusting the phase shifts of the branch impedances using the mechanical or electronic switches. So in this case, the interphase power controller, that means the in the same phase, okay, interphase. So this power control action is done because it is a series connected controller, okay, of active and reactive power consisting in each phase. of inductive and capacitive branches subjected to a separately phase shifted voltages. The active and reactive power can be set independently by adjusting the phase shifts and or the branch impedances, because just adjusting the phase shift of the branch and impedances using mechanical electronic switches. Next is the thyristor controlled braking resistor. Okay, so it is a shunt connected thyristor switch resistor. Okay, this one, this TCBR is a shunt connected thyristor switch resistor, which is controlled to aid, that aid means to help to stabilize a power system or to minimize the power acceleration of the generating unit during disturbance. That means when there is a disturbance, suppose some fault has occurred, okay, some contingent analysis, contingent situation, when fault occurred, then what happens if a fault occurs, one particular transmission line has been disconnected. So under that conditions, it can happen that the particular transmission line which is disconnected, the other transmission line will be carrying the power, but in that case the power which is flowing to the other conductor will increase to a higher value, okay, and this can result in transient disturbance. Okay, so transient analysis. Okay, so there is a question of transient stability. Okay, so whether the system will be able to be stable or not even after the disturbance. So that is why in these cases these braking resistors are used, thyristor controlled braking resistors, which actually are connected in parallel to the line, okay, which control the which is controlled to stabilize the power system to minimize power acceleration of a generating unit. That means resistances will be connected, okay, so that if any extra power flows to the line, then it will bypass through that particular resistor. Okay, because it is connected parallel, so it will draw that particular excess current through it. Okay, because obviously it will have minimum resistance compared to the impedance of the line, so it will be drawing that amount of excess current through it. Okay, so that the whole system can be, you know, saved from that particular disturbance. Okay, so that's it for our today's lecture. Okay. So if we recap, so in this particular lecture we have discussed about the Tsscs, okay, because previously we have discussed about the StatCom, okay, StatCom. Then we have discussed about the difference between the StatCom and the SVC, how StatCom is advantageous over SVC, that is static work compensator. Then we have seen the static synchronous series synchronous compensator Tssc, and basically just the operation and capability of Tssc. Okay, and to see that Tssc and StatCom are very similar, only difference is that StatCom is connected parallel, Tssc in series, and we have seen the transmitted power versus transmission angle characteristics. Okay. Okay. Then we have seen the control range and VA rating also of the Tssc, how it varies and how to take the VA rating. Okay. Then today we have discussed that the difference between the series capacitor and the normal series capacitor and the Tssc. So why Tssc is advantageous for extra high voltage lines. Okay, and then we have seen also another type of a series capacitor, which is the Thyristor series capacitor. Okay, and how does it operate, and how the switching is done, and how the voltage of the capacitor is obtained. And we have seen the UPFC, the combination of the UPFC. So we will dig into more UPFC later on. Okay, how the performance of the UPFC is there, because basically it is the combination of the series and shunt synchronous compensator, that's STATCOM and Tssc. Okay, the combination. Still, the more it will be used in many cases where adverse situations are there, when where the application of both are required. Okay, and there are some advantages and disadvantages of UPFC as well. And then we have seen some other kind of fact devices also.